So you'll recall from pre-calculus when you just looked at different types of functions, such as rational functions or certain trig functions, that graphs were not continuous. You talked about continuity in the sense of graphs, and it was kind of defined as, well, if you have to pick the pencil up off the paper when you're graphing, it's not continuous. So here's the tangent function, this dashed function, and you see that it's not continuous for where cosine x is 0, and that is going to be at odd multiples of pi over 2. So these are all different branches of tangent x that are not connected. And then this solid blue graph is 1 over x, so that's a rational function, and it's in 2 pieces. It's discontinuous at x equals 0. So we're going to see a rigorous definition as to why these functions aren't continuous. And we're going to be able to determine if a function is continuous just by the formula, not by looking at breaks in the graph. So the definition of continuity is based on limits. So a function is continuous at a number a in its domain if the limit as x approaches a of the function actually equals f of a. So it's implied that this limit exists and that f of a is defined. So if you think back to section 2.3 when we evaluated limits of polynomials and rational functions by direct substitution, that's why we could do that, because polynomials and rational functions are continuous at every point in their domain. So that's why we could just plug numbers into the function to find the limit. So there's different classifications of discontinuities. If you look at this rational function that we've looked at again and again, this whole at the point 1, 2, is an example of a removable discontinuity, because you can define this function to be defined when x is 1. I can define it to be defined as y is equal to 2 with a piecewise function, and then I've removed the whole. So I'm making a piecewise function out of it, which are handy things to use when you're talking about limits and continuity. And I've said, okay, when x is 1, just make y 2. And now that whole's gone. So that's an example of a removable discontinuity. It's just a hole. Here's an example of another type of continuity called a jump discontinuity. So this is the signum function, and notice it's really giving the sign of a function. of a number, its input. So it jumps from this horizontal line at y equals 1 down to the horizontal line at y equals minus 1. And even though it's defined at x equals 0, it's not equal to either one of these pieces, notice. But I can't redefine any one of these points and make it continuous. I still have these 2 separate branches. So this is called a jump discontinuity, but you can't remove it. So notice that the reason this guy is not continuous, not just looking at it graphically, but thinking about it algebraically, the limit does not exist at x equals 0. The limit from the left equals minus 1, but the limit from the right equals 1. So that limit doesn't exist, therefore it can't be continuous. And here's an example where I have an infinite discontinuity. So I have a vertical asymptote. Clearly I can't redefine any value of x to make it continuous. And the reason it's an infinite discontinuity is because it's an infinite limit. So there is the concept of one-sided continuity. That's where the limit from one side exists. So if a function is continuous from the right, the limit from the right exists and is equal to f of a. And likewise, if it's continuous from the left, the limit from the left exists and is equal to a. So if you look at this function, graphically, This is continuous from the right because the limit from the right as x approaches 0 is f of 0. But it's not continuous from the left because the limit from the left, notice, is minus 1 as x approaches 0, but f of 0 is 1, not minus 1. So there's also the concept of being continuous on an interval. So a function is continuous on an interval if it's continuous at every number in that interval. So here's a word example of this function defined on minus 1, 2, the x interval minus 1 to 2. So minus 1 is open. So this is, looking at the graph, it's clearly not continuous on this interval. The reason being there is this jump discontinuity here. So let's look at the rigorous reason why it's not continuous. So let's look at the endpoints. The limit as x approaches 2 from the left equals f of 2 because I have that filled in endpoint. So I can say this function is continuous on the interval 0, 2, where 0 is open and 2 is defined and included. If we look at this piece, this is also continuous from the left at 0 because as x approaches 0 from the left, the limit exists and is equal to f of 0. So this function's continuous on the interval open 0 to close 2, and it's continuous on the interval open minus 1 to close 0, but it's not continuous on the entire interval.